Good afternoon, AP. I hope you guys are all in good health as you're watching this video. What I want to talk about today is the fundamental theorem of calculus. So today's lesson was so super important because it has the word fundamental in it. That's honestly not why it's super important. They call it the fundamental theorem of calculus because it's kind of like intuitive. It kind of makes sense when you say it. So the first part of the fundamental theorem of calculus is this. Basically, if I take the derivative of an integral, I get the same thing out. Basically, the derivative undoes an integral. So a derivative undoes an integral, and an integral undoes a derivative. The second piece of the fundamental theorem of calculus is a little bit newer to us. We already knew the first piece. What's newer to us is this. If I take the integral from a to b, which means the area under the curve from a to b of some function that we call f of x, if I want to evaluate the definite integral, if I want to know, hey, what is the exact area under that curve? The exact area under the curve is going to be the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. So basically, I'm going to take the antiderivative or take the integral and evaluate it at the upper bound, which is b, and then subtract it from the evaluation at the lower bound. So let's go ahead and go over a couple of rules first. I guess I can't click that. Okay. All right, so a couple of rules here. Basically, number one, as long as you can find an antiderivative, you can find a definite integral. So as long as the antiderivative exists, you for sure can find the area under the curve from one segment to another, so from one interval to another. There's a little bit of new notation involved. So we've been talking about the definite integral from a to b looking like this. So the definite integral of f of x dx, we say it's equal to this. We say it's equal to capital F of b, which is the antiderivative evaluated at b, minus capital F of a, which is the antiderivative evaluated at a. Some notation that you might see is this. You might see that it's equal to capital F of x evaluated from a to b. This is saying the same thing. These two things are the same. So let's go ahead and actually one more thing here. You guys might, I don't know if some of you guys are thinking this, you might be thinking, hey, whatever happened to C? A proof of what happened to C actually is proven in the fundamental theorem of calculus. If I evaluate this function, technically what I'm going to get is f of b plus c minus f of a plus c. So you can see that if I distribute the negative in here, you can see that the c's are going to cancel. And so I'm just left with f of b minus f of a, which is the fundamental theorem of calculus. Okay, let's move on to an actual example because I kind of feel like you just need to practice these. All right, so the first one, I want to know what's the integral from 1 to 2 of x squared minus 3. So the first thing that I'm going to do here is I want to take the integral, take the antiderivative of x squared, which is x to the 2 plus 1, which is 3, divided by 2 plus 1, which is 3. The integral, or the antiderivative, of negative 3 is going to be negative 3x, and I'm going to use that new notation. I need to evaluate this from 1 to 2. Well, the first thing I'm going to do, and remember 2 is b and 1 is a, I'm going to evaluate it at b. So to evaluate it at b is this right here. I'm going to evaluate it by plugging in 2 to the first piece and plugging into the second piece. So we're just plugging in 2. After that, so this is f of b. I need to subtract it from f of a. Well, a is going to be everything evaluated at 1. So I'm going to say minus, and notice how I put parentheses here. I put parentheses here because you're going to see I'm going to actually use distributive property. This is one of the biggest mistakes that I'm going to see this year on integrals is forgetting to distribute the negative. So if I distribute the negative in here, I'm going to get, if I evaluate, 8 over 3 minus 6 minus a third, and notice it's going to be plus 3 because a negative times a negative is a positive. So if I evaluate this all the way, I'm going to get negative 2 over 3 as my solution. All right, let's move on to the next one. So the next one says, hey, find the integral from 1 to 4 of 3 radical x with respect to x. Well, I don't really know that much about that, but what I could do is use properties of integrals to reevaluate. So I'm going to move the constant out front here, And I'm going to rewrite square root of x as x to the 1/2. In fact, you might remember this strategy from when we first did derivatives. Let's go ahead and use the fundamental theorem of calculus. Well, the antiderivative, or the integral of x to the 1/2 is going to be x to the 1/2 plus 1 is 3/2 divided by 3/2, and keep that constant out front, which is 3. I'm going to evaluate that from 1 to 4. All right, well, what I'm going to get here, in fact, I actually used a little keep it, switch it, flip it. I rewrote 3/2 by keep it, flip it, switch it, since it's in the denominator, as 2 over 3 times 3 times x to the 3/2, and the 3's cancel. So now I want to go ahead and evaluate 2x to the 3/2, evaluated from 1 to 4. Okay, so in order to do this, fundamental theorem of calculus says I'm going to say f of b, which is 2 times 4 to the 3/2, minus, and be careful with parentheses here, f of a, which is 1. So if I go ahead and evaluate this using what I know about exponents, 4 to the 3/2, just a little side note here, 4 to the 3/2 is the same thing as the square root of 4 cubed, or it's the same thing as the square root of 4 cubed, same thing. All right, and we're going to get 14. So you might wonder, okay, how do I do this in my calculator? Unfortunately, my screen is not completely sharing, so I'm just going to draw it out for you, I guess. It's pretty easy. All you're going to do in your calculator is this. Let me draw a calculator. Okay, all you're going to do in your calculator is you're going to go here and you're going to press math. And you're going to go to 9, which says fn int. And then you're going to get this. It's going to look like this. It's going to be like me, and something like this. You're gonna get something that looks like this, provided your calculator is old enough, which is new enough, which I think it is. You're literally gonna plug the integral in. So for example, if I had the previous integral, which I think was from -1 to 4, I already forgot. Oh great, I already forgot. My memory is not very good. 3 radical x, okay. Of 3 radical x, you're just going to put 3 radical x in there, and then make sure you put it in with respect to x, and then you just press enter, and it's literally going to give you the integral. If you want to know what it is in a fraction, just press math frac. And we'll go over that when we go back to class the other day. All right, so there's only a couple more examples here. I'm just going to kind of talk through the other ones. This one right here, just like when we first learned how to do derivatives, we don't know anything about quotients. We don't know anything about products. And so in order for me to take an integral at this point in my life, I need to just write it as a monomial. I need to write it as something in terms of one term. So that's what I did here. I divided everything by 2 x to the 1/3, and then I used what I know about integrals in the fundamental theorem of calculus. D is a really interesting case. You can make D very, very difficult to solve by creating it in terms of a piecewise function, which is what we did afterwards. We made a piecewise function out of it. Really honestly, guys, the fastest way to find the integral of an absolute value is honestly to graph it, or to make a table. Basically, an absolute value function is literally just a piecewise function of 2 linear functions. If I know that this function is linear, I know the area under the curve is really simple. If I want to find the area under a linear function, it's really going to be just finding the area of a triangle. So what we did here is we graphed 2x minus 1, and we got this graph here. If I want to know the integral from 0 to 1, really I'm just asking, hey, what's the area under the curve from 0 to 1? And we can see here that the area under the curve from 0 to 1 is going to be the sum of these triangles here. Well, the sum of the first triangle is going to be 1 times a half times a half. So think base times height divided by 2. Next one is going to be base times height, which is a half times a half divided by 2, or times a half. So if I add those up, I get a fourth plus a fourth, which is 1/2. And so actually, the summation, I guess it is a summation, the integral from 0 to 1 actually is going to be a half. And we can get it really quickly. Now let me show you how to get it not so quickly. To get it not so quickly, we could rewrite x, the absolute value of x minus 1 as a piecewise function. We could say, hey, that is the image of 2 lines that switch at a half. Basically, you can take the negative for this side, and you can take the positive for this side. The negative is going to be when x is less than a half, and the positive is going to be when x is greater than a half. After that, I have a piecewise function. We can add them together. We're going to say, hey, I want to know what's the area under the curve from 0, which is my lowest bound, to the transition point, which is a half, which is going to be this piecewise function. And then I want to know what's the area under the curve from a half to 1, which is right here. That's my other piece. And so in essence, this is a lot more business than we really have to do. We're going to have to take 2 integrals to find this answer. I really don't think that that's probably the best use of your time. And so I would say draw a picture for sure when you're going about doing that. All right, let's go ahead and move on. It actually just said I have low disk space. So I think we're going to go over this last problem later because I think my video is going to go out. All right, I'll see you guys.